You remember in our last class, we were talking about this idea of Landau theory. That is a theory that's based on order parameters rather than on any microscopic model of the world. Right? So we are temporarily pretending like we don't know that the world is made out of atoms and molecules, and we imagine that there are just order parameters. And so then we say, well, the free energy must depend on the order parameters somehow. So let's set up the ways that it might depend on the order parameters. And we do that based on these ideas of smoothness of functions and symmetry. Right? And so then we can set up the possible form of the free energy function and then minimize it, right? And see how can the minimum of the free energy, what's the optimum value of the order parameter, how can that change when we change the coefficients in the theory? Okay, so the example that I started with on Monday was for magnetism. Oh, here I have to connect the iPad to write with. Whoops, I clicked on the wrong thing. Share iPad. Okay, here it comes. All right, so we were setting up the Landau theory for the magnet. And in this approach, the order parameter is the magnetization M. And then we said, well, the free energy, the total free energy is a free energy density times the volume. So the free energy per volume, let's call it little f. And that's something that we could expand as a power series, because any smooth function can be expanded as a power series. So as long as m is small, we could write it as a series in this form. And the argument on Monday led up to this sort of expression, right? And we said the lowest order dependence on m for small m would have this quadratic term and a fourth order term. There could be higher order terms also, but they'll be smaller. They're off in the dot, dot, dot. Right? And then, in principle, all of the terms could depend on temperature, but I claimed the interesting thing would happen when the quadratic coefficient passes through 0. And so we put the expression for the quadratic coefficient to be this a prime times temperature minus T0, the temperature at which this thing passes through 0. And then we can say, well, the other coefficients, they don't do anything special at the same temperature. So let's just assume that they are constant with respect to temperature. All right, so that gives us the F0 and B0. Okay, and then based on this idea, we can say, well, what happens to the free energy as we vary temperature? And we got this set of plots, right? That for temperature above T0, the free energy looks like a parabola, like that. So this is the free energy as a function of m. And at t equals t0, we get that the free energy is some really flat fourth order minimum, like this. Okay, this is free energy as a function of m. And then for t less than t0, our minimum breaks up into two separate minima like this. And so now the minimum could be either here at plus m0 or here at negative m0. So then we could plot what is the minimum and see how does the optimum value of m depend on temperature. Okay. So we would then get a plot for m at the minimum as a function of temperature. And that plot is 0 for all temperatures above T0. And then it's the square root law for temperatures below T0. And this kind of a trend is equivalent to what we found from doing the mean field theory. Right? So this is a similarity between what we had doing mean field theory and what we get from this Landau theory that's based purely on symmetry with no microscopic information. Now, at the end of the class, I already talked about why we would think that these coefficients are positive, right? That this one is normally positive because there's more entropy at higher temperatures. This one could be positive or negative. If we're going to stop the series expansion here, it better be positive, all right? But under some circumstances, it could be negative, and then we would have to include the sixth order term. Okay, so those were where we left off last time. Now, there was another question that I didn't answer, right? And the question had to do with what if there is a magnetic field, right? So what happens if there isn't a perfect symmetry between spin up and spin down, right? And in that case, the magnetic field selects one of these things as the preferred state, right? So we wouldn't be able to say there's no even terms in the expansion. Okay. So let's think about that now. Okay, so we'll say, what if there is a magnetic field? And I'll qualify this question by saying, what if there is a small magnetic field? Okay, I care about a small magnetic field because I might hope that this theoretical approach can give information about that, right? This theoretical approach is assuming that m is small. We assume m is small, and the only way we're going to have m is small is we must assume that the field H is small. if the field H were big, then M might be something big, and the power series wouldn't really work, right? I mean, the power series would need to include, you know, some huge number of terms. Okay, so what do we do if there's a small magnetic field? That's where we might hope to get some prediction out of Landau theory. All right. Well, in that case, we would say that the symmetry between plus m and minus m is broken by the field. That is, we can no longer assume that the free energy has only even terms. It might have odd terms. So, what are some of the odd terms that it might have, right? Well, it could have a term that looks like H times M, okay? That would be a perfectly reasonable kind of a term, right? Because if H has one sign, it favors a certain sign of M. If H has the opposite sign, then the opposite sign of M. And in fact, let's write it as negative H times M, because that way H positive and M positive gives a favorable negative free energy, right? And likewise, H negative and M negative gives a favorable negative free energy. Okay, so these things are favored by a term like that, free energy. Okay, so something like this would be a perfectly reasonable extra term to add to the free energy. What else could there be, right? Well, there might be something like negative H M cubed, right? That has the same properties, right? That if H is positive and M is positive, you get a favorable negative contribution, right? And vice versa. Or it could be something like negative H cubed M, right? Or it could be negative, you know, H to the fifth, M to the seventh, right? Or anything with odd exponents on both of these factors. Now, all of these things are possible. Given that they're all possible, what's the biggest, right? What's likely to make the most important contribution, right? Well, remember, we're assuming that H is small and M is small. So in that case, the biggest term is the one that has the lowest powers, right? Because the high powers make the term extra small, right? A high power of a small thing is even smaller, okay? So this is the dominant term for H and M small. Okay, so we would want to add that to our theory. Right? So when we write out the free energy density, we'll say F is now this F0 minus HM plus 1/2 a prime t minus t0 m squared plus 1/4 b0 m to the fourth plus dot, dot, dot. Right. So in this way of writing things, people usually write the terms in order of increasing powers. So, here's the 0th power, the 1st power, the 2nd power, the 4th power, etc. Okay, now what can we do with this? Okay, well, let's say we want to know, suppose, for example, suppose we are in the disordered phase. Okay, so suppose t is greater than t0. Okay, and we put on a magnetic field, H not equal to 0. Okay, well, then we could ask how much magnetic order is induced by the field. Okay? So let's calculate the M that is induced by H. The way we do that is to say, well, as always, we want to calculate a minimum. So we take the first derivative and set it equal to 0. Okay? So that means negative H plus A prime T minus T0 M plus B0 M cubed equals 0. All right, well, this is a cubic equation. It looks hard, okay? But we can make an approximation to solve it, okay? Remember, we're assuming that H is small, and therefore that M must be small. So here we have a term that's the first power of M. Here we have a term that is the third power of M. That should be extra small. Okay, so we could neglect that one. We will make an approximation to neglect this for small m. And if we neglect that, then the equation becomes really easy to solve, right? Then it's just a linear equation. And the solution is just m is h over a prime t minus t0. So this is a prediction for how much magnetic order is induced by the applied field at a temperature above T0. So how much order is induced in the paramagnetic phase, the disordered phase. Right? And so a plot of that is like this, right? That it's just m as a function of h, it's linear, okay, with a slope that depends on temperature. So the slope is 1 over a prime t minus t0. Okay? So at high temperature, the slope is really small. And then this is lower t, and then just above T0, we get a very high slope. right? So this would be T, whoops, slightly above T0. Okay, so this is the same kind of thing that we saw when we were doing the mean field theory, right? Remember when we were looking at M as a function of applied field, right? We had plots that looked like this, right? We calculated this hyperbolic tangent behavior, and we had M as a function of H, like that, right? And we looked at what was the slope right there, right? And the slope was getting bigger when we got closer and closer to the critical point, okay? So here, it's the same kind of thing. It's just that we're zooming in on this part of the plot, and we don't get the whole behavior for larger fields. And if we want to say what's the slope, that gets the name of the susceptibility. That is chi, is the derivative of M with respect to H at H equals 0. Right? So this tells us if we apply a little bit of a magnetic field, what's the slope, right? How much magnetic order do we get in response to a little magnetic field? And so our prediction from Landau theory is that this is 1 over A prime T minus T0. So if we wanted to express this in terms of critical exponents, this is proportional to T minus T0 to the negative gamma power, where gamma equals 1. So that is the same critical exponent that we calculated in mean field theory. So this whole story is coming out consistent with what we did for mean field theory for the Ising magnet, right? Even though we're not talking about magnetic spins, we're just thinking about the smoothness and symmetry of functions, still we get the same kind of predictions for the trends for small m. We don't get everything, but we get the same predictions for the trends when m is small and when h is small.
So, Jonathan, which theory came first?
Which theory came first? That's an interesting question. I don't actually know the history when it comes to magnetism in particular. I think that the more microscopic theory came first for magnetism. I associate that with Pierre Curie, with early models for magnetism, and then Ising's work was a particular simplified version of that. So that was, well, I'm going to mix up the history, I think around the 1920s or so. The work of Landau was not originally motivated by magnetism. I believe he was mainly interested in superconductivity at the beginning. And so the idea with superconductivity is that was a case where people really didn't know what was the microscopic order parameter. And so all they could do is just make up some order parameter and say, how could the free energy possibly depend on the hypothetical order parameter for superconductivity? Right? And then the microscopic theory of superconductivity, that is the BCS, Bardeen-Cooper-Schrieffer theory of superconductivity, that came later.
Okay, thank you.
I'm not actually going to talk about superconductivity here, but let's talk about the gas to liquid transition. Right? So for the gas to liquid transition, we want to do the same kind of thing. That is, we want to say, let's just make up an order parameter and think about how the free energy might depend on that order parameter. Right? And so we'll say the order parameter should be something small, and then we can make a power series expansion in it. Right? So what could our order parameter be? Right? Well, the first guess would be maybe the order parameter could be volume, V, or this could be volume per molecule. That's a pretty good idea. The trouble is that it's not small, right? If we are working with an ideal gas, this is something really big. And so we wouldn't want to be expanding about a small volume state, right? A small volume state would be like a black hole, right? It would be an extremely dense kind of a situation. So don't want to do that, right? So what about expanding about the density? Expanding in the density, right? So we could say, let's think about the density rho, which is 1 over V. So that's the molecules per volume. This would be an expansion about the ideal gas, right? Because the ideal gas is the system where the volume is really big, so the density is really low. This is not a crazy thing to do. This is a reasonable thing to do. But the problem with doing it is that the transition is not really close to the low density limit, right? That the critical point occurs at a pretty high density. It's pretty different from the ideal gas. And so instead of doing that expansion, we could say just that we know there is some critical density. There must be a critical density or a critical volume.
Is density
VT.
defined as N over V or 1 over V? The definition of the density.
Oh, this is meant to be a lowercase. That's my lowercase v.
Oh, okay.
So that is the same as the number of molecules divided by the uppercase v. I realize it's hard for anyone else to interpret my handwriting for the difference between uppercase and lowercase v. Okay, there must be some critical volume, a lowercase v critical. Okay. So let's define delta volume to be the volume minus the critical volume, okay? And we could expand in powers of delta V. This actually works out, okay? And I wrote up kind of all the steps of doing this sort of derivation in the book in section 4.2. And I'd like you to read it rather than me going through it, because there's sort of a bunch of steps there. So I'll say section 4.2. All the steps are basically equivalent to what we do for the Ising magnet, but we don't have a perfect symmetry between positive and negative delta V. That is, there isn't really a perfect symmetry between extra high volume per molecule and extra low volume per molecule. So there isn't a perfect symmetry between gas and liquid, right? So, you know, in the Ising case, there is a perfect symmetry between spin up and spin down, right? Those two things really are just reflections of each other. Not exactly right with the gas to liquid transition. And so I go through a whole bunch of steps in that section, and please take a look at that. But you can see the argument runs basically the same way. And so it gives basically the same predictions for the critical behavior, that is, for the behavior close to the critical point. And so in particular, it gives the same exponents, the same critical exponents for liquid gas as for Ising. So that means that we would say that the difference of volumes, the liquid volume, I'll say the gas volume minus the liquid volume, is proportional to Tc minus T, whoops, switch back please. Tc minus T to the beta power, where beta is 1/2, right? And the compressibility, that is the derivative of volume with respect to pressure, is proportional to T minus Tc to the negative gamma power, with gamma equals 1. So these are the same kinds of trends that we found for the Ising model, and here they're showing up in the liquid gas transition because they're coming from the same kind of power series expansion. So this, can be regarded as, a unified treatment that applies to both of these phase transitions and can apply to other sorts of phase transitions also, as we'll be getting into later on in the semester. Now, let me mention a couple other things of extra properties of doing this theory, extra features of doing this sort of theory. One sort of feature is that you can think about what happens if there is a non-uniform order parameter? That is, suppose that we go back to the magnetic system and we have an M which depends on position. So it's an M of R. It's a different magnetic order in different parts of a sample. What do we get for the free energy then? Right? Well, for one thing, the free energy depends on M and M depends on R. So the free energy locally must depend on position. Right? We could say there's a free energy density that depends on position.
Jonathan,
Please.
I just like to interrupt you. Can we apply similar ideas on solid to liquid transition?
Yes, and I'll be talking about that later on. So I'll get to solids later on in the semester. But yes, absolutely, there is a similar idea. There is an order parameter.
But the problem is in gas phase, we have only translational motion. So we don't need to care about the rotational motion and vibrational motion. But in solid, we have all three kind of motions. And even in liquid, it's possible to have translational and vibrational motion. So then how can we apply these ideas?
I'm going to postpone talking about solids for a little while. And that's going to be a later chapter coming up. Okay, so the point is, right, we have the free energy density, which depends on M, and M depends on R. So there's a free energy density that depends on position. Okay, so then the total free energy, isn't just the volume times the free energy density, because the free energy density is different in different places. It must be an integral of the free energy density over all the different positions. Okay, so the free energy must be now an integral over the whole volume of F of M of R. All right, so we could say the integral over the whole volume of F0 plus, well, a half A prime T minus T0 M of R squared plus a fourth B0 M of R to the fourth plus higher order terms. So this is one way that position comes in, right? That now instead of just having one single M, it's M of R depending on position. And so now we have to be integrating over all the positions. Okay? So this is one generalization of the thing that we've done so far. But there's an extra part of the free energy also. Okay, so here, this stuff that I've written, right? This all is the free energy associated with a particular value of M. And I'm adding it up for M here and M here and M here and M here, right? All the different positions. Okay? But there might be some extra free energy that comes from the derivative of M, the gradient of M. So we'll say that whoops, wrong pen, that spatial derivatives of m of r give some extra free energy. So spatial derivatives, that means derivatives like dm dx, dm dy, dm dz, right? If m is changing as a function of x and y and z, those changes might cost extra free energy. So how much extra free energy? Well, we could try to make up something for that following the same style as everything else we've done in Landau theory. That is, just by thinking about symmetry and smoothness of functions, right? That is, how could the extra free energy possibly depend on derivatives like this? Well, one thing is we could say, let's characterize these derivatives by a vector. Right? So let's consider the vector of gradient of m. Okay? So this is the vector which is dm dx in the x direction, and dm dy in the y direction, dm dz in the z direction, right? This is what you learn in multivariable calculus courses, right? As one of the derivative operators that can operate on a function. Right? So we could say, well, how could the derivatives of m enter into the extra free energy? Well, we don't want a term that breaks the symmetry, right? We want a term where x derivatives and y derivatives and z derivatives all enter in a symmetrical fashion, okay? That is one constraint on how it could enter the free energy, right? Another constraint is that whatever we construct better be a smooth function of these derivatives. So so that requires symmetry and smoothness. And another feature, of course, is that the extra free energy must be a scalar. We don't have a vector free energy. So the extra free energy could be something that is proportional to this gradient of m quantity squared, right? The magnitude squared of this vector. That is to say, gradient of m dot gradient of m, right? This is a perfectly reasonable thing. This is the most common way that derivatives could enter into the free energy density. They enter in with some coefficient. Typically, people call the coefficient 1/2 k. Right? So 1/2 k on both of those things. Right? And this is then an extra term that goes into the free energy integral. Okay, so we get a free energy integral, which is the integral over all r of f0 plus 1/2 a prime t minus t0 m of r squared plus 1/2 b0 m of r to the 4th power, plus those higher order terms, the non-derivative terms. And then there could be this extra thing, the gradient term, 1/2 k times the gradient of m quantity squared.
Excuse me. Does
Okay.
the length of the gradient of M satisfy the condition of smoothness?
Okay, so what Zheng is asking about is, what about a term like just this thing by itself, right? So this magnitude of the gradient of m by itself. And the answer is no. It violates the condition of smoothness, okay? This counts as not smooth or analytic. And one way to see that is, if you wanted to write out an algebraic expression for this, this magnitude is the square root of dm dx squared plus dm dy squared plus dm dz squared. Right? And the square root spoils the smoothness, right? The square root makes things to be not analytic, right? That right, if we consider that these derivatives are all small, and then we put in a slight derivative, right, that the square root would give an infinite slope, right, which violates the constraint of well-behaved non-singular functions.
Okay.
And so this is forbidden from the theory for that reason.
Okay, thank you.
Mm-hmm. By comparison, a term like the gradient of m to the 4th power, that is allowed, but it's smaller. Right? It's smaller because it has more powers of m in it, and it has more powers of the derivative. And so if m is changing slowly as a function of position, that's something smaller. Likewise, if we have the Laplacian of m, quantity squared, right? That also is allowed, but it's smaller because it is a second derivative of m. Okay. Now, I guess the last thing I want to say about Landau theory in general, another feature of Landau theory is that it allows us to consider other types of order parameters. That is, other kinds of mathematical objects. the order parameters that we have talked about so far are scalars. All right, we have a scalar, which is the M in the Ising model, or a scalar, which is the delta V, the V minus VC for the liquid gas. There are a lot of other physical problems where the order parameter is a different sort of mathematical object. Okay? So there are problems where the order parameter is a complex number. For example, for a superconductor or a superfluid. And I believe that was Landau's original motivation. Okay. There are other problems where the order parameter is a vector. This could be in other types of magnets, where the magnetic moment might not just be up or down, but maybe it could point in any direction in three-dimensional space. Or, as we'll get into later in the semester, there can be problems where the order parameter is a tensor. And I'll be teaching you about tensors this semester, but this is what's required for a nematic liquid crystal. A smectic liquid crystal actually has a complex number for an order parameter. So one important part of theoretical physics is thinking about, in any particular problem that we're working on, what kind of order parameters do we have? And what sorts of mathematical objects are they? And depending on what we're working on, it might be that there's one order parameter, or maybe there are 2 or 3 different order parameters which interact with each other. Okay? And then we want to figure out what can the free energy be expressed in terms of whatever order parameters we have. Right? So the order parameters could be different kinds of mathematical objects, but the free energy is one kind of mathematical object. It's a real scalar. Right? And so we want to figure out, how can we make a real scalar free energy out of whatever sorts of mathematical objects we're working with. And so this is the basis of a lot of what theoretical physicists do. Okay? And so, one thing that students sometimes get hung up on when they first start seeing theoretical physics seminars. Okay, so when you go to the weekly seminars for the AMLCI or the physics department, right? And if there's some theoretical physicist who's talking, the guy will often say something like, "Oh, well, in my problem, I have such and such order parameters. Therefore, I constructed this free energy." And he puts it up on his PowerPoint. Okay. And then all the students think to themselves, "What do you mean you just constructed this free energy? Did you just make this thing up?" Right? So the students are wondering that, but they're too scared to ask, right? But the answer is, yeah, actually he did kind of just make this thing up, right? But he made it up following these rules of symmetry and smoothness. And so that makes a rules for how the free energy might possibly depend on the order parameters. And then you can actually get meaningful predictions out of that, right? So that's part of how people do theoretical physics. One word for this, I'll just tell you one word as the last thing in this class. A vocabulary word for this style of theory is phenomenology. Phenomenology. I hope I said phenomenology. I guess I spelled that right. So phenomenon means something that you see, right? And so that's embedded here, right? So the word phenomenology means just making up a theory based on what we can see, that is order parameters, without knowing about what are the fundamental ingredients in the world, the atoms or molecules or electrons or whatever it might be. And so this is one very common style of theoretical physics, which comes up a lot in the study of liquid crystals, but also other kinds of materials as well. And so it's something that you will probably be seeing a lot of in your graduate career at Kent State. Okay, I will stop here and I'll be glad to answer any questions, either about this subject or about the homework or about anything else that's on your mind. Thanks.
Thank you. To describe magnetic liquid crystal, I think in addition to a complex number, we still need a tensor to describe it, right? Because a complex number only describes the translational symmetry of this magnetic liquid crystal, but we still need a tensor to describe the orientation.
Correct. I should have said that. Thank you.
Another question. I still don't get why the length of the gradient of M is not smooth. I think square root of X is a smooth function, right?
Not at X equals 0. It's smooth everywhere else, but not at X equals 0. So suppose you have some, G of X is the square root of X, okay? And you want to know what's the derivative of that, right? So dg dx is whatever it is, 1/2 x to the minus half, right? So 1/2 square root of x, okay? So at x is 0, dg dx goes to infinity, right? Okay. And so that's what spoils the smoothness.
Okay.
Right? And so if you make the plot of g of x versus x, that looks, well, it doesn't really turn downwards like that. It looks like this, right? It's nice and smooth everywhere except right there, right? And right there, it has infinite slope.
Okay.
And this infinite slope breaks the assumptions of Landau theory.
Okay, thank you.
Mm-hmm.